brighter, but all 100 watts, not 80 or 120. And so this means that these particular kinds of supernovae are what we call standard candles. And if you know how bright something is, then you can determine how far away it is relative to other supernovae. And so what they were able to plot was essentially, we could tell how big the universe was when they were exploded. That's the redshift. We can tell that from the spectrum of light. And then they used the brightness of these supernovae to essentially tell how far away they were, or alternatively, how far in the past they had exploded. And what we had expected was something like this black line, that a supernova that went off when the universe was 2/3 its present size would have a particular brightness. But the points there are showing you that instead, a supernova that went off when the universe had a certain fraction of its current size was actually about 25% fainter than we expected. And that was the indication that the expansion of the universe is not slowing down due to gravity, but is in fact speeding up. And that's what led to the Nobel Prize. So why is this a strange phenomenon? Why is this a mystery? Well, whenever you have any kind of object, every time you've taken any object and you've thrown it up and dropped it, whenever you throw up a ball, as soon as it leaves your hand, it's moving upward, but what's happening? It's slowing down due to gravity. It's attracted to the center of the Earth. As soon as it leaves my hand, it starts to slow down, and because I can't throw very hard, eventually it reaches a maximum height and then falls back down to Earth. And every time you've thrown a ball up, that's what's happening. And that's because gravity is attractive. But what the universe is doing is sort of like, imagine I throw this ball up, and initially it starts slowing down due to gravity, but then at some point, instead of continuing to slow down and eventually hitting a maximum point and falling back to Earth, safe to say we've never seen that in our everyday experience. But that's why the acceleration of the expansion, the speed up of cosmic expansion, is a mystery, because it confounds our understanding of gravity. So what could be causing this speed up of the expansion of these? And we basically think there are two possibilities. The first possibility is that the universe is filled with some kind of stuff that gives rise to a kind of repulsive gravity. Gravity is usually attractive in our everyday experience, in the solar system, in our galaxy. But perhaps when we're talking about things on cosmic scales, there is some additional stuff in the universe. It's not dark matter, it's not atoms, it must be something else, which has the property that it makes things repel from each other, and therefore speed away from each other. We now call this dark energy. And we think that the universe is 70% dark energy. That's one possibility. The other is that maybe something strange is going on with gravity when we get to cosmic scales. Again, in the Earth, the solar system, our galaxy, gravity obeys Einstein's theory of general relativity. It's attractive, of course. But again, perhaps when we get to very large scales, gravity behaves in a different way, in such a way that things can accelerate away from each other. So that's the second logical possibility, is that there's something going wrong with our understanding of gravity. So we now have this picture that's been put together just over the last 10, 15 years, that 95% of the universe is dark, doesn't emit with a light or interact with light. So the stuff we see in our everyday world, stuff made of atoms or more fundamentally quarks, that's only 5% of the universe. So the stuff we're trying to figure out the nature of, primarily here at Fermilab and elsewhere, that's only 5% of the universe. The stuff that we know about, the laws of physics that we know about. We think 25% is this dark matter. It's not made of atoms. It's made perhaps of some new elementary particle. And that's the stuff that's holding galaxies and clusters of galaxies together. and is the engine by which galaxies with gravity, by which structure forms in the universe. And then we think the dominant component of the universe, 70%, is this dark energy, this gravitationally repulsive stuff that's actually speeding up the expansion of the universe. Dark energy is not something we observe in our everyday life. It has no tangible effects, again, on terrestrial scales. It's much too dilute, too weak a force. So it would only come into play on cosmic scales. So one interesting thing is, I said that the universe today, we think, is about 70% dark energy. That's if you look on the right-hand column, about 20% dark matter, about 4 or 5% atomic ordinary matter. But if we go back in time, then those relative amounts of those different components will change. We think that as the universe expands, dark matter becomes more dilute, ordinary matter becomes more dilute, because as things get, as the distance between them gets bigger, the density, the mass per unit volume goes down. But that doesn't happen with dark energy. So since dark energy is dominating today, as the universe, we think that the density of dark energy hasn't changed very much from today to earlier times. And that means if I go back in time when the universe was denser, higher density of dark matter and ordinary energy is relatively less important. So if I go back to a time 9.5 billion years after the Big Bang, the middle column there, then we think the universe was about 50% dark energy, 43% or so dark matter, 7% ordinary matter. And if I go even further back in time to just a billion years after the Big Bang, then we think dark energy was only 1%. Dark matter was the dominant component, 84%. Ordinary matter, about 15%. And this is important because remember I showed you that movie of structure forming by gravity. That only works in a universe where the bulk of the stuff is dark matter. Once dark energy takes over, becomes more dominant than dark matter, structure can no longer form because dark energy is this repulsive force pushing things away from each other, where gravity was the thing pulling them together. So we think that before, a few billion years, the universe actually was slowing down. Gravity of dark working on with colleagues here and around the world for a number of years called the Dark Energy Survey.
At our basic goal to make a map of the universe, trying to understand the history of the expansion of the universe and the history of a clumping up of the universe in order to get at the properties of dark energy or whatever is causing the universe to bleed. And so what we've done is we've built a camera for a telescope in Chile, and we're now conducting surveys, taking pictures, snapshots of things like 300 million galaxies over about 1/8 of the sky. And we're also taking snapshots of certain polar regions of the sky, which we go back to going in the same direction roughly every week to discover more of these supernovas. The Nobel Prize work is based on observations of just a few tens of galaxies. In this project, we're going to have observations of thousands of supernovae and hundreds of millions of galaxies. So we started, the survey started in late August of 2013 with definition observing season. It's supported in the United States by the Department of Energy and the National Science Foundation Development, George Saxelauer Network, and we are trying to spend the partners. We also have 4 video research partners survey agencies. And using this map to try to understand the history of the cosmic expansion and structure. The 4 primary techniques that we're trying to use. Technique A is study of the population of galaxies. Technique B is to count how many of them there are in a given volume of space. The technique of gravitational lensing that I mentioned before, look at the distortion of the shape of distant galaxies as their light passes around the distant dark matter. A third technique is to measure the distribution of galaxies in space called large-scale lensing. And the fourth is beam separation, or quantum acceleration. In this project, we measure precisely the measurement of the I'll just mention one of the techniques. We use gravitational lensing, so again, the idea here is measuring shapes of very distant galaxies. Light from a galaxy will travel towards us around a distribution of dark matter, based on the dark matter associated with the galaxy, clusters of galaxies, and as it travels towards us, the light path extends. That's what Einstein's general relativity told us. And that light then produces a slight distortion of the shape of these galaxies. Before I showed you very pronounced distortion of the shape.
We call strong lensing, but that only happens to a minority of distant galaxies if they happen to be just near the line of sight to some foreground galaxy. All galaxies, all distant galaxies get weakly distorted, weakly lensed. And so we can measure this by using the shapes of these 200 million distant galaxies. And that will give us information on dark energy. So in order to do this project, we've built an international collaboration. We have 400 scientists from around the world. The project is led by a team here at Fermilab in the US, but we have collaborators in England and in Europe, Brazil, and Australia. And we use this telescope. This is the Blanco telescope on Cerro Tololo Inter-American Observatory. This is operated by the National Optical Astronomy Observatory. It's in the northern Andes Mountains of northern Chile. So inside, these are 3 different telescopes. The biggest one is that one with the silver dome in the middle. If you go inside that dome, this is what you see. So on the left, that big structure is the telescope itself. And what you see here is the mirror of the telescope. It has a diameter of about 4 yards across, 4 meters. And so light comes in from the sky, bounces off of that mirror, and then goes up into our camera, which is this thing in the upper right. It actually goes through 5 different lenses, which focus the light onto a big digital camera that's about this big around. So this is what the actual focal plane of the camera looked like. It's 570 million pixels. That doesn't sound like so much today. You know, our iPhone has 10 million pixels, but 10, 12 years ago, sounds
Mm.